We are done with conservation laws. So we're starting a new topic, but since we have a week off, I'm not going to do that today. So we're just going to do sort of a review day. I'll give you time to work on stuff, and then I'll go through it. What you really should do, what'll help a lot, is do your best to do these problems. Talk to each other as you go, talk to me as you go, or whatever. But then just make sure at every step that your answer matches my answer. It's a way to find the things that are confusing you about these problems. Okay, before I get into that, let's talk about where we're at in the class. The most pressing thing is the withdraw deadline is tomorrow. Okay? So if you think a withdrawal is, a possibility for you, I would strongly recommend making an appointment with the advising office to talk to them about it, because sometimes it can have like financial aid implications and stuff like that. So, for most people, you're in this class, you're not thinking about that kind of stuff. But for anybody who is thinking about a W, that's something to consider. You recently turned in weekly assignment 3, and I have not graded that yet. But I think every other thing is now in the grade book, including the late stuff that people have emailed to me. So right now you can look at your grades, and it should have everything you've given me. If it doesn't, let me know and I can fix it. But it's a good chance to sort of see where your grade is at. It should be a pretty good reflection of where you're at in the class. Remember, these grade cutoffs are going to be at or very close to 90, 80, 70, 60. So if you look at your overall percentage in the class, you can see pretty clearly, what kind of grade you're talking about right at this point. Okay. There is still room to make up some ground. I'll still take work if you give it to me. For the most part, I'm not going to take huge clumps of don't give me 30 assignments or whatever in the last day, or whatever. But I'll still take late stuff if you haven't turned it in. Also, the last exam, if you haven't done so well on one of the previous exams, the last exam can replace that score. So doing well on the 4th exam can give your grade a boost, But it's definitely getting to the point where it's not unlimited ability to change your grades anymore. You know what I mean? So we have less than a month left in this class. So I guess it's time to, put some stock in what that grade is at right now, I guess, And then, of course, there's no school at all Thursday and Friday. I don't know this, but I assume the building is going to be locked, so I don't think you can even come here and study or whatever. Okay. Okay. And I have my stuff canceled for tomorrow, so I won't be here tomorrow. That doesn't affect you guys very much. I don't have office hours on Wednesday or anything, but and there's no labs this week. Next week, we are going to get back to labs. It's been a long time. Remember labs? So next week, we're going to do our last lab exercise. Then we're going to have our final lab exam. And then in the last week, we'll do some stuff. But we're pretty much getting towards the end of labs. All right. Anybody have any questions about grades or homework or anything right now? Yeah.
Is exam free next?
I thought you were going to ask me about that one assignment again.
Time.
What time is the final?
I thought exam 3 was next week.
Oh, is it? Oh,
I thought it was like Tuesday.
oh shit. Oh no, that got away from me. Let me look. No, that's important. Oh my gosh. Well, if it is, man, I haven't said anything about it to anybody. So I might put that off a little bit because I sort of feel like I didn't give people enough heads up on that. Shoot, it's always something, you know? Yeah, December 3rd. Shoot. Okay, well, what are we going to do then? I guess we'll probably move exams to the week of the 9th to the 13th. I guess we probably will. We're not going to do exams next week because I didn't even tell people before they left for Thanksgiving break about that. Okay.
Professor,
Yes.
could you remind us again when the finals are? I know it was 2 dates. Was it
Yes.
Tuesday and Wednesday? But I forgot those times. The 19th or the 18th.
Okay, so I have a Monday, Wednesday class and a Tuesday, Thursday class. The Monday, Wednesday class, that's going to be Wednesday at 11. And the Tuesday, Thursday class is Thursday at 2. And you can feel free to use either one of those. It doesn't, if the one on Wednesday works better for you, feel free. If the one on Thursday works better, feel free. Okay? Any other questions right now? Okay, well, I just want to write up a few different types of problems and give you time to go through it, talk to each other, talk to me, and then I'll go through it after I give you some time. So that was loud. So example, the first one. So let's say we have a horizontal surface. And we have these two rolling carts that are connected by a cable. Let's say this one has a mass of 40 kilograms. And this one has a mass of 15 kilograms. And we have a 25 Newton force down, a 30 Newton force to the left, and 150 Newton force to the right. And we want to do three things. First, calculate the acceleration vector. Second, calculate the force vector. Applied to the 15 kilogram by the 40 kilogram. And then third, calculate the force vector applied to the 15 kilogram by the ground. Okay, so the first step is to calculate the acceleration vector. Do these two things have the same acceleration or different acceleration?
Same.
Same, yep. If they were different, there'd have to be a pulley in the problem of some kind. So, and then, so since they have the same acceleration, we're going to start by isolating the whole system. So take a few minutes and see if you can work through that. Compare answers to each other. Talk to people around you or whatever. But just get a little practice. So we're going to do a free body diagram of the whole thing. So there's the free body. And I guess I'll first draw the weights that the forces that were given. There's the 30 that way, the 25 this way, the 150 this way. And then there's a weight force down. The total mass is 55. So 55 times 9.81 is 539.55. And then there's the pushing force from the ground. I'll call that N total. And that's everything. What are we going to say about the acceleration? So whenever you're doing the first body you isolate, all we have to think about is this moving along X or along Y? In this case, it's moving along X, so our acceleration vector is just going to be A0. Okay. And so what we're looking for is we're trying to calculate that acceleration vector. Well, this is it, but we don't know what that variable A is yet. So the rest of our job is just figuring out what that A is so we can plug it in. Okay. So Newton's second law says -30, 0 plus 0, -25 plus 0 in total. 1, 2, 3. The weight 0, -539.55 plus 150, 0 is equal to the total mass of 55 times the acceleration A0. We're just trying to calculate that A, so you can see from this that the Y equation doesn't get us closer to what we're looking for. So the X equation says -30 plus 150 is equal to 55A. Solve for A and you get positive 2.18. Now plug that into our expression for the acceleration vector, and we get that the acceleration vector is 2.180. Or going this way at 2.18. Any questions about that? All right, now that we have the acceleration, now we can isolate individual bodies. You can see that B and C both are asking for forces applied to the 15. So that makes sense as the one we're going to isolate. So now draw a free body diagram of the 15 kilogram cart and go through and calculate B and C. Okay, so free body diagram of the 15. We still have the 30 acting on this one and the 25. We don't have the 150 that's acting on the other one. We have the weight force down that's equal to 15 times 9.81, so 147.15. We have the normal force, I'll call that N15. And then we have the pulling force from the cable. And for this one, we know the acceleration now because these have the same acceleration. So this acceleration vector is 2.180. So now I'll go to Newton's second law. We have negative 30, 0, plus 0, negative 25, plus 0, negative 147.15, plus 0 and 15, plus T0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And then the mass is 15 times the acceleration. Okay, well, the things we're trying to calculate the force applied to the, well, I called it the force applied to the 15 by the 40. I mean, it's really the force applied to the 15 by that cable between them. But that is this force. So we're trying to come up with that force vector. That's for part B. And then for part C, we're trying to come up with the force vector applied to the 15 by the ground. So that's this one. Okay, so the X equation says negative 30 plus T is equal to 15 times 2.18. And so T is equal to 62.73 newtons. And if you leave your answer like that, that's probably a point off the problem because it specifically asked for the vector. So you have to give the direction in some way too. So the force on the 15 by the cable is 62.730. Or in other words, it's in the positive x direction at 62.73. Yeah.
How do you get the 3 at the end of the 17?
Oh, I kept what I had from before. So this acceleration is 120 divided by 55. So 2.1818. So that's how, yeah. Like really when you do, and it wouldn't matter to me if you rounded that off or whatever. I mean, I would never take points off for something like that. But when you're thinking about significant figures, remember that you should always keep as many digits as you can in your calculations and only truncate it to the right significant figures to give your answer, you know? So that's part B. And then for part C, we're going to use the y equation. So that says negative 25 minus 147.15 plus N15 is equal to 0. So N15 is equal to 172.15. And then to plug that into the vector, the force on the 15 by the ground is equal to 172.15. Or it's just an upward force of 172.15. Any questions about that? Okay, now let's say, so another example. Let's say there's a kid on a skateboard. And the skateboard is next to a ramp, okay? And somebody throws a 1 kilogram ball to the kid fast, let's say at 20 meters per second. The kid is initially at rest. And when the kid catches the ball, he's going to move up this ramp some distance because the ball is going to make them both move. And we want to see how high up the ramp the kid and the ball make it, okay? And so we're going to do this in 2 pieces. This is one of those combined problems. For the collision, so for part A, we're going to do the collision, and it says, after the kid catches the ball, how fast is the kid/ball system moving? Let's say that this kid has a mass of 30 kilograms. And then second, what's the change in height up the ramp before the kid and the ball start to roll back down? Okay, so for the collision part A, what do we use for calculations for collisions?
Linear momentum.
That's right. So this is conservation of linear momentum. So take a couple minutes and see if you can go through that calculation to calculate the speed after that inelastic collision. Let me go through this one. So before the collision, we add up the momentums. We have a mass of 1 kilogram times a velocity of 20, 0, because it's moving in the positive x direction, plus a mass of 30 kilograms times the starting velocity of 0, 0, because she is at rest, the girl, this little girl.
Yeah, bro. I feel bad, okay?
Okay, don't feel bad. It doesn't look very much like a girl to me, but okay, so and they stick together after the collision. They have the same velocity after the collision. So after the collision, you can think of it as a single thing with a mass of 31 kilograms. And you can calculate both components, but we know it's just going to be moving along the x-axis. So I'll just write this as v0. And then so we get 2 equations. The x equation says 20 is equal to 31v. The y equation says 0 equals 0, so this is the only one that matters. And so v is equal to 0.645 meters per second. And that's going to be going this direction. Any questions about that? Okay, now the second part of this problem is now we have this 31 kilogram object that's moving to the right at 0.645 meters per second. So now we have to calculate how high that speed is going to carry them up the ramp. Okay, so for part B, what are you going to use for this calculation? You're relating speed to location, and the only forces are gravity and a normal force. So this looks very much like something you'll use conservation of mechanical energy for. Okay, so see if you can use conservation of mechanical energy to see how high up the hill. Okay, so I'm going to call instant 1 when the kid and the ball are at the bottom of the hill, and instant 2 is when they're up at the highest point on the hill. And I'm going to call h equals 0 before the kid gets to this ramp. So instant 1 and instant 2. At the bottom of the hill, the gravitational potential energy is m times g times 0. So this is just going to be 0. Anytime you're at 0 height, it's 0 gravitational potential energy. And then the kinetic energy is 1/2 times the mass of 31 times the speed squared. That speed from before was 0.645. And amazingly, you get 6.45 after. So that's in joules. And then when the person gets up to the highest point on this hill, we're trying to calculate that height. So this is going to be a mass times 9.81 times an unknown height. So I'll just leave that as h. That's what we're trying to calculate. So that's 304.11 times h. And now what about the kinetic energy? Well, what's the speed when this kid reaches the highest point on the hill before the skateboard starts to roll back down? 0, yep. So this is going to be 1/2 times 31 times 0 squared, so 0. And now we can put these into the equation. We have 6.45 is equal to 304.11 h. And so h is equal to 0.021 meters. So just over 2 centimeters of height difference from catching this ball. Any questions about that? Okay, let's do one more conservation of mechanical energy question. So here's the setup. There's a track with a loop-de-loop, and there's a little rolling thing here. And we're going to set this rolling cart in motion by like pinball pulling this plunger back to compress this spring. Okay? And then we're going to send this going. The spring has a constant of 1,000 newtons per meter. And the mass of this cart is 0.1 meters. And so we're going to pull, oh, and let me give you a radius of this. Let's say that the radius of this loop is 0.2 meters.
Did you diagram or not?
Yes,
Yours is bad, you have no.
thank you. Okay, so pull the spring back from its resting length,
I could fix that if I wanted to, but
0.03 meters, so 3 centimeters. Okay, and release it. Does this cart make it around the loop?
That's awesome, mega energy. Awesome.
Okay, so that's the question we're trying to answer. Well, the first thing we have to do is figure out how fast this cart is moving once it leaves the spring. Okay, so for part A, how fast is the cart going after it leaves the spring? What are we going to use for that calculation? Well, this is something you should always remember is we've only talked about springs in one way. So anything involving a spring has to be conservation of mechanical energy in this class. It's just kind of like a practical way to think about it. So use conservation of mechanical energy to figure out how fast that cart is moving when it leaves the spring. Done by the end of class. Again, I'm going to choose an instant 1 and an instant 2. Instant 1, it doesn't matter which one you choose as 1 and 2, but I'll choose when the spring is compressed. And I'll choose my h equals 0 to be the height of this thing, which means that at instant 1 and instant 2, potential energy is just going to be 0. So I'll still put that in here. But the gravitational potential energy at instant 1 is 0. The spring potential energy, that formula is 1/2 times k, the spring stiffness, times x squared. So this is going to be 1/2 times 1,000 times 0.03 squared. And so that is 0.45. And then the kinetic energy, well, we're releasing that spring from rest. So the speed is 0. So the kinetic energy is 1/2 times the mass of 0.1 times 0 squared, so 0. And then after the spring is released, the height is still the same. And so this gravitational potential energy is still 0. Now the spring has been released, so it's back to its resting length. And so the spring potential energy is 1/2 times 1,000 times 0 squared, so 0. And all we have is the kinetic energy, which is 1/2 times 0.1 times v squared. Or we can write this as 0.05 v squared. So now put it into conservation of mechanical energy. You have 0.45 We're adding up all the stuff on the left, setting it equal to the sum of all the stuff on the right. 0.45 is equal to 0.05 v squared. So v is equal to well, v squared is equal to 9, so v is exactly equal to 3. I just made those numbers up. I'll have to remember that. Okay, so the next step is, now this thing is no longer in contact with the spring, and it's moving at 3 meters per second. So now we want to calculate the second step is how fast would this thing be going if it travels through that full circular motion. Okay, so so now how fast is it moving at the top of the loop? What are we going to use for this calculation? Conservation of mechanical energy again, because we're trying to find a relationship between a location and a speed. This time the gravitational potential energy is going to matter. We can ignore the spring potential energy. The spring is back there and gone, you know. So see if you can work through this and calculate a speed for this thing at the top of the loop. Again, this is going to be conservation of mechanical energy. I'm going to have my instant 1 be at the bottom of the loop, and my instant 2 at the top of the loop. At the bottom of the loop, that's my h equals 0, so the gravitational potential energy is 0, because the height is 0. The kinetic energy is 1/2 times 0.1 times 3 squared. So that is 0.45. Yep. And then at the top of the loop, how much higher is this thing when it's at the top of the loop? We do, because I gave you the radius of that loop. So it's going to be 2 times that radius. So we have the gravitational potential energy is the mass, 0.1, times 9.81 times 0.4. And so that's 0.3924. And the kinetic energy is 1/2 times the mass times the speed squared. And we don't know what that is, so that's 0.05 v squared.
How is it 0.4 and not 0.2?
Because the radius is 0.2, and so the diameter, the height from the bottom to the top, is 2 of that. Okay, so the equation says 0.45 is equal to 0.3924 plus 0.05 v squared. And so what we get here, when you solve for v squared and then take the square root, v is equal to positive 1.152 meters per second. Okay, do we know, so we know that it has some speed still at the top if it's held in a circular path, but we don't know yet whether it's going to stay on that loop. That's because this speed, that could be the track holding onto the wheels, as it goes, but the track doesn't really do that. So the last thing we have to check is whether the track is pushing on the wheels or whether the track would have to be pulling on the wheels, which is impossible. Okay, so here's how we're going to do that. So now we're going to do a circular motion problem, and we care about the top of this circle. The velocity is this way. The centripetal acceleration is this way. There's no tangential acceleration because the height isn't changing. The centripetal acceleration magnitude is v squared over r. So that is, yes?
I think you forgot to take the square root of that answer.
Oh, I did. I said to do it and then I didn't. Thank you. So this is 1.073. Sorry about that. Okay, so centripetal acceleration is 1.073 squared divided by the radius of the circle, which is 0.2. So that's 5.76 meters per second squared. And as a vector, that's pointing down. So the centripetal acceleration vector is 0, negative 5.76. And now think about a free body diagram. There's a weight down of 0.981 and then a normal force pushing, that R. And what we're going to do is from Newton's second law, we want to see whether that R is positive or negative. As long as it's positive, or 0 would be fine too, then this will stay on the ramp. If that R ends up being negative, then this won't stay on the ramp, it'll fall off. So Newton's second law says 0, negative 0.981 plus 0, negative 5.76. No, what am I doing? So it's the weight and the R. So this should be 0, negative R. And these are equal to the mass, 0.1, times the acceleration vector that we got up here. And so that's 0, negative 5.76. The y equation says negative 0.981 minus r is equal to negative 0.576. And so R is equal to so R is equal to negative 0.405. And so, that R force can't pull, so this will fall off. Anybody have any questions about that? Okay. Well, have a good Thanksgiving. So we will not do the exam next week. I'll think about that and I'll put it on D2L today when we'll do it. And yeah, see you Tuesday.